The conical pendulum. Here we have a conical pendulum, and we can show the forces acting on the pendulum. We have the weight mg acting down, and the tension T in the string acting up in this direction. We can show some other dimensions. If I draw the axis of rotation here, then the string is at an angle theta to this axis, and the pendulum is following a circle of radius r. The chaeroplane ride shown here is basically several conical pendulums, and you'll see from this shot that the adult here is hanging at the same angle as the small child next to him. As we play the clip, you'll see that even empty chairs and the loose seat belts are all hanging at the same angle as those with adults in. So clearly mass has no effect on the angle. To understand why that is, let's look a little bit more closely at the forces involved. So here we have the mass of the conical pendulum, and the forces are the weight mg acting down, the tension T acting at an angle theta to the vertical. We can resolve the tension into its vertical and horizontal components. The vertical component across angle theta will be T cos theta, the horizontal component T sin theta. The vertical component is exactly balancing the weight, so we can say that T cos theta is equal to the weight mg. The horizontal component is providing the centripetal force, so we can say that T sin theta is equal to the centripetal force mv squared over r. Combining these, we get this expression, and we can cancel the t's, the m's, and also sin theta over cos theta is tan theta, giving us tan of the angle theta is equal to v squared over gr. So mass does not appear in this equation. The angle made by the bob does not depend on the mass of the bob, but only on the speed v of the bob and the radius of the circle r swept out. If this was not the case, the empty chairs would be colliding with the ridden chairs on the chaeroplane.